relationship with security. For example, many of us would be really upset if a company that we trusted with our personal data, like Apple, Amazon, eBay, even Gmail or YouTube, had their databases hacked and our information compromised. But how many of us have a password called password? Or a bank PIN code as your birthday, like my wife. And I tell her to change it every day. Security is only as good as the weakest link. And right now, the weakest link is human ignorance, like weak passwords or an IT administrator forgetting to close off a port and allowing a hacker in. But what if the weakest link in security was the actual encryption algorithms that protect our data? It might seem like something from Mission Impossible 3, but DNA computing could pose that risk. Let's start with a basic form of cryptography called steganography. Steganography was invented in ancient Greece to encode messages, and it's really not cryptography as much as it is hiding a message within a message. For example, in World War II, the Allies used steganography to hide messages in the mail. They sent letters to each other, but the real content of the message was hidden inside a period within the message. And the receiver would blow up that period to magnify what the real message would be. And the 1944 Battle of Normandy was actually planned using this type of encryption. So in 1999, researchers in California had the electric idea to use DNA computing to try to replicate this sort of theory. And what they did was they used the human DNA to encode a message. Human DNA is made up of 4 molecules represented by the letters C, A, G, and T. And so what they did was they took sequences of 3 molecules to represent a letter. So for example, A was CGA and B was CCA. And they would genetically engineer a strand of DNA to encode a message. And the example I have here that I'll pass around is the message is Toastmasters. So they genetically engineered a strand of DNA with a message, and then piled on top of it 31 million other strands of DNA, which still is only like this big, and piped it onto a letter, and sent it in the mail. And then they prayed that the USPS would actually deliver their message to a researcher in Boston. And the researcher in Boston took out the message, looked inside that period, found through 31 million strands of DNA the actual message and decoded it. So this proved that there actually was practice to using DNA in cryptography. But in real life, this form of cryptography, steganography, is not used. RSA encryption is a type of computer encryption that has been used for over 25 years because it has the unique ability to be very easy to encode data, but very difficult to decrypt it. At the root of RSA encryption is a key. And that key is just a number, but it's a number made up of 2 prime numbers. A prime number is a number that isn't a multiple of any other number. For example, 3 and 5. So say your RSA key was 15. In order to break RSA encryption, you would have to find out that 3 times 5 made 15. You'd have to reverse engineer 15. That's very easy to do for a small number. If I gave you a bigger number, 4 digits, 5 digits, RSA encryption keys usually span 200 digits long. It'd be very difficult to crack that and could take years. And so in 2005, researchers at Southern Taiwanese University decided to use human DNA and some of the previous research that had been done, like the example that I passed around, to try to crack RSA encryption. And they did it. Using a DNA computer that they engineered that I cannot explain in 5 to 7 minutes, they actually made a DNA computer to crack RSA encryption. So that, in other words, they decomposed 15 into 3 and 5. And then they tried a 4-digit number, and they were able to do it relatively easily. And then a 6 and a 10-digit number, and they were able to crack that too. And based on their results, they theorized with logical proof that they could do any number in a finite amount of time, which would really rock the security world and the basis that most websites encode their data. In comparison, a 210-digit number for RSA encryption takes 75 years using one of your personal laptops to decode. And even the world's biggest supercomputers cannot or have yet to crack a 300-digit long RSA key. The researchers in Southern Taiwanese University said that they could do it in a finite number of hours, with one caveat. They would need a lot more DNA. Could you hold on to this? The amount of DNA they would need, if this represented that amount in gallons, only this amount of water in the world exists. So while they could do it in a finite amount of time, it would take them a lot more resources in order to do it. Computers in the 1950s took up huge rooms using silicon chips, and today, 60, 70 years later, we have that same amount of computing power in a little box in our laptops or on our smartphones. DNA computing, while very small, it exists everywhere. It's very plentiful. It's very easy to find on all of our bodies. While it's very small and very efficient at doing computing, such as cracking RSA security in a matter of hours, it still needs a big amount of room. And so, for now, your personal data is safe, as long as your weakest link isn't your birthday. Madam Toastmaster.